Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the combustion process. It's often instructive to study the combustion of a fuel by assuming that the combustion is complete. A combustion process is complete if all the carbon in the fuel burns to carbon dioxide, or the hydrogen burns to water, and all the sulfur burns to sulfur dioxide. That is, all the combustible components of a fuel are burned to completion during a complete combustion process. Conversely, the combustion process is incomplete if the combustion products contain any unburned fuel or components such as carbon, nitrogen, carbon monoxide, or OH. Insufficient oxygen is an obvious reason for incomplete combustion, but it is not the only one. Incomplete combustion occurs even when more oxygen is present in the combustion chamber than is needed for complete combustion. This may be attributed to insufficient mixing in the combustion chamber during the limited time that the fuel and the oxygen are in contact. Another cause of incomplete combustion is dissociation, which becomes important at high temperatures. Oxygen has a much greater tendency to combine with hydrogen than it does with carbon. Therefore, the hydrogen in the fuel normally burns to completion, forming water, even when there is less oxygen needed for complete combustion. Some of the carbon, however, ends up as carbon monoxide or just as plain carbon particles in the products. The minimum amount of air needed for the complete combustion of a fuel is called the stoichiometric or the theoretical air. Thus, when a fuel is completely burned with theoretical air, no uncombined oxygen is present in the product gases. The theoretical air is also referred to as the chemically correct amount of air, or 100% theoretical air. A combustion process with less than the theoretical air is bound to be incomplete. The ideal combustion process during which a fuel is burned completely with theoretical air is called the stoichiometric or theoretical combustion of that fuel. In actual combustion process, it is common practice to use more air than the stoichiometric amount to increase the chances of complete combustion or to control the temperature of the combustion chamber. The amount of excess air is usually expressed in terms of the stoichiometric air as percent excess air or theoretical air. For example, 50% excess air is equivalent to 150% theoretical air, or 200% excess air is equivalent to 300% theoretical air. Of course, the stoichiometric air can be expressed as 0% excess air or 100% theoretical air. Amounts of air less than the stoichiometric amount are called deficiency of air and are often expressed as percent deficiency of air. For example, 90% theoretical air is equivalent to 10% deficiency of air. The amount of air used in combustion process is also expressed in terms of the equivalence ratio, which is the ratio of the actual fuel-air ratio to the stoichiometric fuel-air ratio. The complete combustion process with no free oxygen in the products is called theoretical combustion. The theoretical combustion of machine is predicting the composition of the products is relatively easy when the combustion process is assumed to be complete and the exact amounts of the fuel and air used are known. All one needs to do in this case is simply apply the mass balance to each element that appears in the combustion equation without needing to take any measurements. Things are not so simple, however, when one is dealing with actual combustion process. For one thing, actual combustion processes are hardly ever complete, even in the presence of excess air. Therefore, it's impossible to predict the composition of the products on the basis of the mass balance alone. Then, the only alternative we have is to measure the amount of each component in the products directly. A commonly used device to analyze the composition of combustion gases is the offset gas analyzer. In this device, a sample of the combustion gases is connected and cooled to room temperature and pressure, at which point its value is measured. The sample is then brought into contact with a chemical that absorbs the carbon dioxide. The remaining gases are returned to the room temperature and pressure, and the new volume they occupy is measured. The ratio of the reduction in the volume to the original volume is the volume fraction of the carbon dioxide, which is equivalent to the mole fraction if ideal gas behavior is assumed. In offset analysis, the gas sample is connected over water and is kept saturated at all times. Therefore, the vapor pressure of water remains constant during the entire test. For this reason, the presence of water vapor in the test chamber is ignored, and data are reported on a dry basis. The volume fractions of the other gases are determined by repeating this procedure. Okay, that's all for this task. Thank you very much and see you next time.